The following lecture will cover sections 210 to 211 from the text. If you remember from the last lecture, we covered formal charges in bond line structures, lone pairs in bond line structures, and then we introduced resonance. And we discussed the rules for drawing resonance structures and what the curved arrows represent and how to draw them. In today's lecture, we're going to discuss the patterns in resonance so that we can draw resonance structures given a molecule. So there are 5 patterns that we're going to be looking for, and we're going to learn how to draw the arrows for each of the 5 patterns. Learning these patterns is critical to drawing resonance structures. You not only need to be able to identify the pattern, but also to know how to draw the arrows for each pattern. And there's a couple rules that we're going to go over for each one. The 5 patterns are allylic lone pair, allylic carbocations, lone pairs of electrons adjacent to carbocations, pi bond between 2 atoms with different electronegativities, and conjugated pi bonds in a ring. The first pattern we're going to learn to draw resonance structures for is an allylic lone pair. So we need to be able to identify an allylic lone pair and then learn the arrows for that pattern. So we need to first be able to differentiate between a vinylic and an allylic lone pair. All right, both of these are positions relative to a carbon-carbon double bond. Vinylic position is one of the atoms in the carbon-carbon double bond. It could be any group or lone pair, and an allylic position is a group or lone pair that is on a carbon adjacent to the carbon-carbon double bond. So if we look at from a different perspective with the carbons drawn in, anything on the carbon involved in the double bond is vinylic, and things that are adjacent would be allylic. So let's look at another example of lone pairs. So look, everything is relative to the lone pair or relative to the double bond. On an atom adjacent, that's the nitrogen, right? You have a carbon-carbon double bond. There's a hydrogen. There's a hydrogen. On an adjacent atom, we have a lone pair. That's allylic. And then this lone pair up here, that's not adjacent to a carbon-carbon double bond, so it's not allylic. That's not vinylic either. A vinylic lone pair would look something like this. Right, if we had a carbon, let's just draw some other groups there. So let's say that's a hydrogen. That could be another carbon. Here's a carbon, carbon. Call that carbon, hydrogen. Call that anything we want. So if we have a lone pair on the atom in the double bond, that's vinylic. If your lone pair is on an atom adjacent to the double bond, that's allylic. So that's the first thing you need to be able to identify is the allylic lone pair of electrons. All of the lone pair electrons in the following example are allylic. So remember, it's adjacent. The lone pair is on a carbon or atom adjacent to the carbon-carbon double bond. Here's your carbon-carbon double bond. We have an atom adjacent, and we have a lone pair. We have a carbon-oxygen double bond. We have a lone pair that is adjacent to that pi bond. We have a carbon-nitrogen double bond. We have a lone pair on an atom adjacent to the pi bond. This lone pair would be considered the vinylic position for our purposes right now. We have a carbon-oxygen double bond and we have a lone pair that is on an atom adjacent to the pi bond, so that's allylic. And if your lone pair is on an atom in the double bond or involved in the pi bond, that's vinylic. So for this pattern, we're always going to draw two curved arrows to get to our resonance structure. When the atom with the allylic lone pair has a negative charge, the charge is delocalized with the lone pair. So the negative charge is following the lone pair. Our arrows always go. The tail of the arrow starts on the lone pair of electrons. See, this is an allylic lone pair. It's on a carbon atom that is adjacent to a carbon-carbon double bond or any pi bond. The tail of the arrow always starts on the lone pair. And remember, it goes atom to bond and then bond to atom. So the first arrow, remember, atom to bond. And the second arrow is always going to go bond to atom. And now if we wanted to go convert our resonance structure back to the original, this is still an allylic lone pair. Atom, tail of the arrow starts in a lone pair, atom to bond. And the next arrow, bond to atom. This pattern, or this set of arrows, these rules, will work for every allylic lone pair. All right, let's look at another one. We have a lone pair of electrons that is adjacent to a pi bond. So the tail of the arrow starts on the lone pair, atom to bond, and the next arrow goes bond to atom. Now let's say we wanted to convert our structure back. We go atom to bond, bond to atom. Make sure you can see how the electron pair moves and how it ends up on the adjacent atoms and how our charges get assigned. If the allylic atom is neutral, then it will become positive. And if the allylic atom and the receiving atom will become negative. So we have a neutral molecule here. Our allylic atom is neutral. So here's your allylic atom. And watch how it becomes positive. We take our electron pair, atom to bond, bond to atom. You see how the lone pair turns into the pi bond, and the electrons from our pi bond become the lone pair. So the allylic atom becomes neutral, the allylic atom becomes positive, and the atom receiving the lone pair becomes negative. Let's look at another one. So our allylic atom is neutral. The lone pair goes atom to bond, bond to atom. And we can see the lone pair from the nitrogen becomes this pi bond. Nitrogen now has a positive formal charge. And our pi electrons are now deposited onto the oxygen atom, giving 3 lone pairs. So an oxygen with 3 lone pairs and 1 bond is a negative formal charge. So again, atom to bond, bond to atom. It works every time for this pattern. You have to know how to draw those arrows and identify an allylic lone pair. Following the examples, I'd like you to stop the video and give these a try on your own. When you're done, you can check back and see how I solved the problem. Identify the allylic lone pairs, draw the arrows and the resonance structures. Be sure to include the formal charges. All right, hopefully you were able to give this a shot. The first thing is identifying the allylic lone pairs. Let's look at our first molecule. We have a lone pair of electrons that is adjacent to a carbon-carbon double bond. So this is an allylic lone pair. Now we have to draw the resonance arrows. Remember, the tail of the arrow always starts on the lone pair, the atom, and it's going to go from atom to bond, and then bond to the atom. Now in our six-membered ring, we saw the lone pair is being dumped into that carbon-carbon bond. That's going to create a pi bond. And the pi electrons that were in that carbon-carbon double bond are now becoming that lone pair. If you need to, draw the hydrogens in. You can also draw your carbons in if you need to. Carbon, carbon, carbon. The next one, we have a lone pair of electrons that's on an atom adjacent to a pi bond. So it doesn't matter which pair of electrons we decide to move. We're going to take the tail of the arrow on the electrons or the atom to bond, and then bond to atom. And this is a case where the receiving atom will become negative and the donating atom will become positive. So those pi electrons are moving up onto the oxygen atom, which gets a negative charge, and there's the oxygen. That pair of electrons was used to make a pi bond, still has that lone pair of electrons, and an oxygen atom with 3 bonds and 1 lone pair gets a positive formal charge. So our next pattern is an allylic positive charge. So again, we're dealing with the allylic position. You're looking for a positive charge that's located on an atom adjacent to a pi bond or carbon-carbon double bond. So here we have a positive charge on a carbon atom that's adjacent to a carbon-carbon double bond. That's your allylic carbocation. Only one curved arrow is needed for this pattern, and it's always the same. We always move the arrow, put the tail of the arrow on the double bond. This is different from the allylic lone pair. For this one, tail of the arrow on the double bond, and we go bond to bond. Now if we wanted to go, and that would give us our resonance structure. If we wanted to go back, bond to bond, and that would give us our original structure. So in each case, the electrons move from the pi bond to the adjacent bond. This pattern is always bond to bond, and you need one arrow for each allylic positive charge. All right, so for a conjugated system is simply any molecule that has multiple double bonds at every other carbon, so alternating single and double bonds. We could draw a single arrow that gives us our next resonance structure, bond to bond. That would give us our next structure. And then we're left with another allylic carbocation, bond to bond, which would give us a third resonance structure. Now, alternatively, you could have combine both of these into one step. So I could move bond to bond, bond to bond, and you would end up with the following resonance structures. So you can do these in multiple steps, or you can do it in one step. For the next example, I want you to draw the curved arrows and the resonance structures for each of the compounds. Don't forget to include your formal charges in the resonance structures that you draw. So pause the video, give this a shot. When you come back, I'll show you the answers. All right, hopefully you've had a chance to try these. All right, we've got a carbocation that is in the allylic position. And every time for this pattern, we're going bond to bond. The tail of the arrow starts on the pi bond, and the head of the arrow goes to the adjacent single bond. So we have to show the movement of the electrons. The pi bond is moved, and we're basically switching, the carbocation is switching places. For our next structure, now we can do this in one or two steps. You may have drawn the first arrow like that to give the following resonance structure. And in this case, we'd see another allylic carbocation, and you could have done a second arrow. And you would have ended up with the following resonance structure. You could have also done it all in one step and drawn two arrows, which would have led you to your final structure. Either way you arrive at the structures, or the final structure is correct. But technically there are three resonance structures for this particular molecule. The next pattern is a lone pair adjacent to a carbocation. This pattern only requires a single curved arrow. And to draw this pattern correctly, the tail of the arrow should be placed on the lone pair to begin with. And the head of the arrow should always be placed to form a pi bond between the lone pair and the positive charge. Let's take a look at an example. So in this first example, we have the lone pair that is adjacent to a positive charge, and the tail of the arrow starts on the lone pair, and the head of the arrow goes to where the pi bond will end up. And this can be undone if you want to go back to your original structure. So in this case, we went from atom to bond. In the next example, we have a lone pair that's adjacent to a positive charge, and the arrow is going to start where the lone pair is currently located, and the head of the arrow is going to point to the bond that exists between the atom with the lone pair and the atom with the positive charge. So we went from atom to bond. Now, if the atom with the lone pair, you notice, has a negative charge, then you end up with charges that cancel, like in our first case. But if the atom with the lone pair is neutral, you're going to end up pretty much just swapping the position of the positive charge. An important point to note. All right, for the next example, I'd like you to give this one a shot. I want you to locate the lone pair that's adjacent to a positive charge, draw the resonance structure with the arrows, and don't forget to include any necessary formal charges. Hopefully you were able to give this one a shot. We're looking for a lone pair that's adjacent to a positive charge. So here's our lone pair that's adjacent to a positive charge. In this pattern, we draw the arrow, tail of the arrow is on the atom. The head of the arrow points to the adjacent bond. And we can see that that lone pair has now become a pi bond. Our nitrogen still has a lone pair. And if your atom with the lone pair is negative, then the charges cancel. So this is now neutral. In the next example, we have a lone pair adjacent to a positive charge. So tail of the arrow starts in a lone pair, head of the arrow goes to the adjacent bond. And if we want to draw our resonance structure, there's the oxygen. We have our double bond. And now the positive charge sort of switches place. The fourth pattern is a pi bond between two atoms with different electronegativities. So we're only going to use this pattern if we have something like a double bond in between carbon and oxygen, or a double bond between carbon and nitrogen, or carbon and any other atom that has a greater electronegativity. So this pattern, we always move the electrons from the pi bond to the more electronegative atom, because electronegative atoms by nature have the ability to attract electron density towards themselves. And in this pattern, it's just the reverse of the lone pair adjacent to a positive charge. So we're basically reversing the last pattern. We're going from bond to atom. And if we go back, we go atom to bond. So this pattern is pretty straightforward. You need a single arrow to draw the resonance structure. So in the next example, I'd like you to give this one a shot. Draw a resonance structure, draw the arrows, and include any necessary formal charges. All right, hopefully you've had a chance to draw the arrows and resonance structures. So the pattern we're looking for is a pi bond between two atoms of different electronegativity. So we have a double bond in between carbon and oxygen. In this pattern, we always put the tail of the electron, the tail of the arrow on the pi bond, and the head of the arrow is going to point towards the more electronegative atom. So we're drawing our resonance structure. We see that the electrons, those pi electrons, have moved up onto the oxygen atom because it's more electronegative. The oxygen will get a negative charge, and that carbon, because we've taken two electrons away from it, is now going to have a positive charge. In the next example, we have a pi bond between carbon and nitrogen, and the electrons from the pi bond should be deposited onto the nitrogen, the more electronegative atom. And now that nitrogen is going to have, drew an extra bond. That nitrogen is going to have two lone pairs, so it gets a negative charge. And the carbon gets a positive charge. The last pattern is a conjugated pi bond system in a ring. So we have alternating single and double bonds in a ring, and each atom in this ring has an unhybridized p orbital that can overlap with its neighbors in order for electrons to be shared. The pi bonds are always pushed over by one position, counterclockwise or clockwise, it doesn't matter, you get the same result. So we can start with The first one, doesn't matter where you start, bond to bond, bond to the adjacent bond, bond to the adjacent bond. And we get the resonance structure. So in summary, we have 5 patterns that we talked about and how to draw the arrows for each pattern. For the allylic lone pair, we needed 2 arrows, and we always went from atom to bond, bond to atom. First one and the second one. For the allylic lone pair, you only needed 1 arrow. It was always bond to bond. For the lone pair adjacent to a positive charge, we went from atom to adjacent bond. 1 arrow, and the next pattern was a pi bond between atoms with different electronegativities. We needed a single arrow going from bond to atom. And the last pattern was our conjugated pi bonds in a ring. So, some problems can be solved using multiple patterns in order to arrive at the same answer. So both examples below are correct. Let's take a look. So let's try to identify a pattern. So the first pattern you might have seen, we have an allylic lone pair. You have a lone pair of electrons that are allylic to a positive charge. You may have seen a pi bond between atoms with different electronegativities. So you have carbon double bonded to oxygen. So let's go with this first pattern, the pi bond between atoms with different electronegativities. So we know that the arrow goes from bond to atom, and if we want to draw the next, based on this, we see that we've got a lone pair adjacent to a positive charge, or carbocation. So we can draw that pattern with 1 arrow. And we end up with our final resonance structure. You may see the allylic lone pair, in which we go from atom to bond, bond to atom. And notice we arrive at the same final answer. So there's no wrong way to do this. However, recognizing this pi bond between atoms of different electronegativities just afforded us a pit stop that gave us another pattern to push arrows through. Section 211 deals with the stability of resonance structures. All resonance forms don't necessarily contribute equally to the hybrid. So resonance stability tells us that the more stable structure will contribute more to the hybrid. There's 3 rules that we're going to follow in order. So the first rule is that the most significant resonance structure is the one that has the greatest number of filled octets. So remember, you can't exceed the octet rule, but you can have less than an octet. And that would impart a positive charge on the atom, like with the carbocation. So let's look. There's no formal charges here, unlike this atom, where the carbon has 3 covalent bonds in an empty p orbital. So this carbon only has 6 electrons around it, right? It's short of its octet. So it has 6 electrons around it, but technically that carbon atom really only owns 3 of those, right? And it needs to own 4 to have a neutral positive, to have a neutral formal charge. So atoms that have an octet are more stable than atoms that have less than an octet. The next rule is that we want to minimize formal charges because charges cost energy. So neutral resonance forms are more stable than charged resonance forms. So here are 3 resonance structures, for example, and the first one is neutral. And the next 2 contain charges. And they both have a positive and a negative charge. So we could say they're relatively equal contributors at this point. However, the best resonance structure or major contributor is the one that's neutral. All right, the next rule is that the more electronegative atom should get the negative formal charge if we have a choice. So let's take a look at the example where we can draw 3 resonance forms for the NCS molecule. So in our first one, we have a -2 and a +1. We have a -1 on the nitrogen, and we have a -1 on the sulfur. So if we apply rule number 2, we can eliminate this one as being the worst because it has the highest charges. We got a -2 and a +1. That's a terrible resonance structure. We would say that it does not contribute significantly to the hybrid. Now we're left with choosing between these 2 structures. We can put a negative charge on the nitrogen or the negative formal charge on the sulfur. The rule tells us that the more electronegative atom should get the negative charge if we're looking for the molecule or resonance structure that contributes most to the hybrid. So nitrogen is more electronegative than sulfur. Therefore, the structure with the negative formal charge on nitrogen is the major contributor to the resonance hybrid. In other structures, the less electronegative atom should get the positive charge. So, for example, if we have an option of putting a positive charge on the oxygen or the nitrogen, right, so the pattern here would be an allylic lone pair. Right, we push those electrons through to get our next resonance structure. And we want to determine which is the major contributor to the resonance hybrid. The atom that's less electronegative should be the one that gets the positive charge if we're identifying the major contributor. And finally, resonance forms that have equally good Lewis structures are described as equivalent and will contribute equally to the resonance hybrid. So for example, all of these 3 structures, 1, 2, and 3, right, we cannot differentiate them with any of the rules that we previously discussed. Right, so none of the structures have less than an octet. They all have the same degree of charges. And all of the negative formal charges are on oxygen atoms. Right? So we can't differentiate any of these. So we say that they are equivalent resonance contributors. So the skill that we need here is, given a set of resonance structures, you need to be able to rank them in terms of their contribution to the resonance hybrid. We're going to rank them from most significant to least significant. And we want to briefly explain why we chose what we chose. So go ahead and stop the video, apply the rules that we just reviewed, and try to determine the major and minor contributors to the resonance hybrid. All right. So let's take a look at resonance structures A, B, and C. Well, if we look at our first rule, we have something that's neutral, in which everything has its octet. In this structure here, everything also has an octet. So this structure, we have a carbon atom that has less than an octet, so we can say that this is the worst. And for our next structure, or next set of structures, right, we can apply rule 2, which states that charges cost energy. So we have charges on this resonance structure, while this one is neutral. So this one here, C, would be the best. or the major contributor to the resonance hybrid. And this one would be okay. That one's in the middle. For the next example, try to draw all possible resonance forms and then indicate the major resonance contributor to the hybrid. So pause the video, give this one a shot, and when you come back, I'll go over the answer. All right, so for the following molecule, there's a couple resonance patterns that we could draw. So we're going to have to draw two additional resonance structures. The first one is if we assume that we see the lone pair adjacent to the positive charge. So we can push those arrows from atom to bond. And we'd end up with a double bond in between the nitrogen and the carbon. We'd end up with a positive charge on the nitrogen, and the carbon would be neutral. The other pattern is if you noticed the allylic positive charge. So we can move the electrons from the double bond into the carbon-carbon double bond, in which this carbon has an empty p orbital, and we'd end up with another resonance structure where we'd have a positive charge on that carbon, a double bond for nitrogen, as a lone pair. So if we push the electrons any other direction, we'd end up with the starting structure. So we want to evaluate the contribution of each of these structures to the resonance hybrid. So first, we want to try to eliminate anything that has that does not have an octet. So the following two structures, we have a carbon that doesn't have an octet. This structure has its octet, so this one is probably going to be the best. And the structures here, we'll call these A, B, and C. A and C are exactly the same. So we've got positive charge on a carbon, positive charge on a carbon, and a nitrogen that has a lone pair. So in this case, I would say that these are somewhat equal. Or we could say this is a minor contributor, minor, and this is the major contributor to the resonance hybrid. In section 2.12, we're going to further discuss the resonance hybrid and learn how to draw a resonance hybrid given a set of resonance structures. So when we first introduced the resonance hybrid, we said that it was a combination of individual resonance structures. It more accurately represents what's happening with the electron density, because we said that individual resonance structures are imaginary. And the resonance hybrid shows us partial charges on atoms as opposed to full formal charges. Partial charges are more stable than a full formal charge because the electron density is spread out over multiple atoms as opposed to being localized on any particular atom. So that imparts resonance stabilization. So when we want to draw a resonance structure, you first need to draw each of the significant resonance forms, and then we're going to use these dotted lines and partial charges to illustrate the delocalization of electrons. And any non-bonding or lone pair electrons can be omitted. So for example, if we want to draw the resonance hybrid for the following molecule, we see that we've got our two resonance structures, and we're going to delocalize that charge. We can see that the bond is switching places. So we're going to just draw that dotted line in between all of the atoms involved in the delocalization. And we put positive partial charges in place where we had our full formal charges. So I'll do this one with you. So if you'd like to stop the video and try this, go ahead. But I'm going to do this problem. So step one was to draw all of your possible resonance forms. Right, so hopefully you're seeing the allylic lone pair, and we push the electrons from atom to bond, and then from bond to atom. And that's going to give us our next resonance structure. Okay. And if we want to draw the hybrid now, we can see that we had a negative charge that was either on the carbon or a negative charge on the oxygen. And our double bond was switching places. So let's hash out the framework here. We put a dotted line where our double bond or pi electrons were being delocalized through these two bonds. And then we're going to put partial charges in place where we had our formal charges. Partial negative, partial negative. And we can omit the non-bonding electrons in our resonance hybrid. In our last section here in chapter 2, we're going to discuss delocalized versus localized electron pairs. So we need to be able to identify delocalized electrons that are capable of moving, and then also be able to identify localized pairs that are not capable of moving. Delocalized electron pairs are those that we saw in some of our patterns, like an allylic lone pair, or a lone pair that's adjacent to a positive charge. And localized lone pairs, these are your lone pairs that will not participate in resonance, and lone pairs that we did not discuss in any of our patterns. So delocalized pairs are those lone pairs from our patterns that will participate in resonance. So for example, the lone pair in this nitrogen is delocalized because it's on an atom adjacent to a carbon with an unhybridized p orbital. So this carbon is sp2 hybridized. Anytime you have an allylic lone pair, it will be delocalized, meaning it will participate in resonance. And we can see that with our two resonance structures here. For example, pyridine's lone pair is localized even though it appears to be in the allylic position. So, if you have a lone pair that is vinylic or not allylic, it will be locked into a hybrid orbital and it will not participate in resonance. So, do you see how this lone pair, it appears to be allylic, but it is in the vinylic position, so we say that it is localized. The lone pair is not in an unhybridized p orbital, therefore it cannot participate in resonance, and it's actually in an sp2 hybrid orbital. So that's the lone pair right there. It's actually an sp2 hybrid orbital. So the quick and easy way to identify a delocalized lone pair is that you just want to look for that lone pair to be in the allylic position only. It cannot be vinylic or any other position. So let's look at a few examples. We've got 3 lone pairs, and we want to identify if they're localized or delocalized. And remember, delocalized is allylic position only. Everything else will be localized. All right, let's start here. That lone pair, it's not adjacent to a pi system. It's definitely not on an atom in a double bond or pi bond. So it's nothing. It's not allylic, it's not vinylic. So this is localized. This lone pair happens to be in an sp3 orbital. Let's take a look at this lone pair. Well, it's on an atom involved in a double bond or pi bond. So we'd say that this is in the vinylic position, therefore it is localized. It will not participate in resonance. Our final lone pair is allylic to 2 different pi systems. So we have this lone pair on an atom that is adjacent to a carbon-carbon double bond and adjacent to a carbon-nitrogen double bond. So that means it is allylic and it will be delocalized. And there's a few examples of these problems in the homework that you should definitely try.